Epilogue: Determinism: Scenes from the Interplay between Metaphysics and Mathematics by Gregor. The subject of this book is evolution equations, that is a mathematical treatment of motion and time. In this epilogue, we will thus review some scenes from the history of the attempts to describe motion by mathematical means. However, we will begin with a more general question concerning a relation of mathematics and reality, which we will try to exemplify by discussing the problem of motion and its determinism. In the first section, we will recall the mathematical framework of almost all contemporary scientific theory with temporally changing systems. Section 2 shows that to a large extent modern science fits into this framework. In section 3 we will draw a historical line through the discussion of determinism, extending from Isaac Newton to Albert Einstein. In section 4, this discussion will be continued on philosophical grounds. Finally, in section 5, there will be an attempt to eliminate a more encompassing dimension of the problem. As far as the propositions of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. Albert Einstein. This is a well-known, ironically resigned remark by Albert Einstein, completely separates the spheres of mathematical certainty and the reference to reality. Thereby, it not only prevents from the outset a potential conflict between them, but also defeats any possible constructive contact between mathematics and reality. In its content, the remark is indeed beyond reproach, which explains why it, in one form or another, constitutes the last line of defense for natural scientists confronted with a discomforting question: what does your work tell us about reality? At least unconsciously, however, the scientist often assumes that the world, or relevant properties thereof, in fact correspond to its mathematical description. If such a naive realism is probed more deeply, then the scientist can do no better than offer the triumphs of technology as evidence of such a correspondence, while the theoretician, and in particular the mathematician, take cover in the complacent view that he is concerned only with models, and the question of their reality, of their relation and application to reality, falls beyond the bounds of his accountability. Such a strict distinction makes the question of interpreting mathematics with respect to reality easy to dismiss. However, an opposing standpoint needs not directly question Einstein's remark, but instead merely note, and this will be the guiding principle in what follows, that mathematicians and natural scientists have always held and will continue to hold that mathematical propositions refer to reality, and it is almost impossible to understand, let alone stimulate, the ongoing of science without reference to that connection. The interplay of mathematics and metaphysics will be examined here with regard to the problem of determinism, the conflict between freedom and universal determination. The focus is on the philosophical question of whether and to what extent the course of natural events is predetermined. Inextricably bound up with this question of human Inextricably bound up with this is the question of human freedom. While this is certainly true from a historical perspective, insofar as the various historical positions are to be understood in terms of their motives and in their justifications, this is also true from a systematic perspective, insofar as being human is to be understood as the ambivalent state of being simultaneously natural and rational. Determinism is of paradigmatic significance to us here not only because this book deals with one parameter, semigroups, which, as will be shown in section 1, can be seen as the mathematical formulation of autonomous deterministic motion, but also because it is one of the fundamental problems that have been repeatedly discussed and reformulated. It lies at the core of the long-lasting debate on representing nature by mathematical terms. An attempt to look at determinism from the point of view of mathematics can be found in monograph by Dunford and Schwartz. 1. The mathematical structure. A large part of contemporary natural science is concerned with investigating the motion of systems. Motion will designate here and in what follows all forms of temporal change, and is thus a much more general term than mere change of location. The mathematical framework for this investigation can be outlined as follows. The object of inquiry is the motion of a system in time. Time is represented by the additive group of real numbers R, or the additive semigroup R+. We thus use a one-dimensional homogeneous continuum consisting of single points. The system under consideration is characterized by a set Z, the state space, of distinct states Z that belong to Z, whose temporal change is to be determined. The set of all possible states of the system is thus fixed from the outset. For example, the state space of a planetary system may be taken as the positions and velocity or momenta of all planets, or the state space of an ecosystem can be chosen as the number of individuals belonging to each relevant space. 4. The motion of a system is described by the temporal change of states, or in mathematical terms by a function or a t that belongs to R that takes t to zt belonging to capital Z that maps each instant t belonging to R, the real numbers, to a unique state z of t that belong to the space Z. Are relativity, quantum mechanics, and chaos deterministic? It is a frequently voiced opinion that 20th century scientific theory has revolutionized philosophy's view on determinism. In particular, one refers to relativity, quantum mechanics, and chaos theory in this context. In this section, we intend to show that these three are more or less closed, and mathematically codified theories can be integrated into the scheme sketched in section 1. First, Einstein's theory of relativity elaborates in its special relativistic part indeed a new structure of spacetime compared with Newtonian mechanics. However, the causal structure is neither globally nor locally very different. To obtain accord with the picture of section 1, you have only to consider the eigensheight for every body or every observer. In cosmology, the standard model uses a global, absolute cosmological time within which matter evolves deterministically. Finally, some of the most famous researchers in the field of relativity and cosmology are very fond of the idea of strict determinism. Compare, for example, 14 and, of course, Einstein himself. Second, quantum mechanics offers a more complex picture. A thorough examination of its various interpretations would lead far beyond the limits of this epilogue. For deeper study, see 20, 32, and 36. In particular, we concentrate on the closed theory of circa 1930. With respect to the question of determinism, one has to distinguish between, roughly speaking, two different time evolutions in quantum mechanics. This is first the unitary time evolution of the individual state, a psi function following Schrödinger's equation. Indeed, there is no better example of an abstract Cauchy problem solved by a group. The state of a quantum system thus evolves deterministically in the sense of section 1, as long as no measurement process takes place. The measurement process represents the second form of time evolution in quantum mechanics, and there has been a long-lasting discussion about the primary probabilities occurring with the measurement process. It is remarkable that the real dissection of the motion due to measurement causes these troubles. As in Aristotle's description, it changes the course of time evolution and is to be discussed as distinct from a mere potential dissection. Interestingly enough, contrast to Kant, the perspective of the observer might here be the reason for a certain indeterminism. Measuring a quantum system, also called reduction of the wave packet or projection, is codified by stochastic time evolution, where the absolute square of the state psi of t can be interpreted as a probability density Born's interpretation. Whether these primary probabilities, which is a weak form of indeterminism, will give way to a more fundamental crypto-deterministic description as a problem of current research. See 36, page 120. Thus, in quantum mechanics, a new state space has been introduced that allows a deterministic theory. Indeed, the fundamental scientific paradigm shifts in the wake of quantum mechanics does not concern determinism, but raises the question of the reducibility of the material world into single, trivially combined elements, as well as the related question of the observer's perspective. This question, only loosely connected to the problem of determinism, is given a negative answer within the framework of quantum mechanics. Each elementary or non-elementary quantum mechanical system is typically a unit that is not to be regarded as consisting of building blocks. In the transition from classical to quantum mechanics, this new concept of the object is much more essential than any change in the notion of causality. This is in the summary version an exemplification of the claim of Ernst Cassirer, presented in his book Determinism and Indeterminism in Modern Physics, which he published in 1936. This work's systematic hypothesis states the answer that the epistemology of science gives to the problem of causality never stands alone, but always depends on a certain assumption as to the nature of the object in science. These two are intimately connected and mutually determine each other. That is, one cannot assume that the object to be investigated is completely given in all its possible facets in order then to examine its causal interactions. Rather, the reverse is true. The inquiry into a particular kind of causality determines what kind of objects will be perceived by the observer. Third, the so-called chaos paradigm, from which quite often far-reaching philosophical conclusions are derived, appears with a few possible exceptions as a disheartened return to classical physics, since an interpretation of or reconciliation with quantum mechanics has proven to be too difficult. This paradigm apparently once again refers to objects in nature as if they behaved like billiard balls. On the level of the objects, there holds this a strict determinism. The only new development is an improvement of the mathematical rigor in discussing the epistemic problem that knowledge of the initial state with finite accuracy gives rise to a dramatically reduced possibility of forecast. Yet this sensitive dependence on the initial conditions, today's completely new insight can already be found in historical examples. Leibniz, for instance, had already described the butterfly effect in his small essay on destiny. And often such small things can cause very important changes. I used to say a fly can change the whole state in case it should buzz around the great king's head while he is weighing important councils of state. And even this effect of small things cause, causes those who do not consider things correctly to imagine some things happen incidentally and are not determined by destiny. For this distinction arises not in the facts but in our understanding. Developments in the concept of object from Leibniz to Kant. We will try to give in this section a concise summary of the philosophical reflections on determinism that followed the rise of modern science and which were best expressed in the works of Leibniz, Hume and Kant, especially the changes in the concept of object and observer, and the relationship will be emphasized here. As early as in Leibniz's work there can be found an omniscient world spirit, claims that everything proceeds mathematically, that is, infallibly in the whole wide universe, to the extent that if someone were to have sufficient insight into the inner workings of things and had enough memory and intelligence to take on and account for all circumstances, he would be a prophet and see the future in the present as if in a mirror. The basis of this picture is the unique universal perspective of metaphysical God, detached from the world but omnisciently observing the whole. Soon after this controversy with Clarke, Leibniz harmonically ordered a universe in which knowledge and being, concept and object, enjoy a pre-established argument, was taken to its foundations under the weight of David Hume's radical skepticism. In his An Inquiry Concerning Human Understanding, Hume repeatedly warns against extending philosophical investigation to questions that lie entirely out of the sphere of experience. While treating the question of causal connection, Hume makes a preliminary decision. He rejects Leibniz's assumption of a pre-existing world of simple substances persisting independently of perception. For Hume, reality consists of perceptions and experience, which is the recollection of past perception. It is thus the individual perspective of any observer that provides the starting point for all further considerations. Under these conditions, there is no logical argument for any kind of causal connection between perceptions. That the sun will not rise tomorrow is no less intelligible a proposition. It implies no more contradiction than the affirmation that it will rise. Accordingly, one cannot differentiate between an expectation supported by natural causality and one stemming from human acts. A man who at noon leaves his purse full of gold on the pavement at Charing Cross may as well expect that it will fly away like a feather as that he will find it untouched an hour after. At the end of this analysis remains the useful belief generated by the power of custom in the causal connection of events. Such belief cannot be rationally justified, but is based on mere feeling. Consequently, mathematics is denied the power to found causal relations between facts. According to Hume, the certainty of mathematical deduction cannot be transferred to the sphere of perception. Nor is geometry, when taken into the assistance of natural philosophy, ever able to lead us into the knowledge of ultimate causes. Every part of fixed mathematics proceeds upon the supposition that certain laws are established by nature in her operations, but still the discovery of the law itself is owing merely to experience, and all the abstract reasonings in the world could never lead us one step towards the knowledge of it. With his skeptical analysis of philosophical reason, Hume has set a standard of reflection that forbade any further uncritical use of metaphysical ideas, even the apparently clear and fundamentally concept of causality. but a rigorous application of his skeptical results made completely incomprehensible the far-reaching success of the mathematical description of physical processes given by Newton's mechanical physics. Moreover, and characteristically enough, the phenomenon of human freedom was also left underdeveloped in Hume's writings. At this point, Kant's critical revolution sets in. On the one hand, Kant not only confirms Hume's skeptical analysis in its full extent, but he takes the argument still further. There is simply no possibility whatsoever for reason to make grounded claims concerning the causality of objects. On the other hand, if reason is not to fall prey to a blanket skepticism, and if one wants to understand the success of the mathematical approach to nature, then the focus of philosophical inquiry must be altered. Thus, the critical question is to be addressed not immediately to things, but rather to knowledge. 9, page 17. The principle of causality now expresses nothing more than a mode of relation between objects and the perceiving subject. Kant's critical determinism is a principle for the formation of empirical concepts, an assertion and a prescription as to how we should grasp and form our empirical concepts in order that they may discharge their task, the task of verification, Objektivierung of phenomena, 9, page 19. This, however, poses the question of freedom in a completely new way. Human action can be regarded from two different perspectives rigorously founded in an analysis of knowledge. As Kant states, a rational being can regard himself or herself from two standpoints. In the first case, it is like if everything an empirical subject and as such subject to universal determinism. In the second case, human beings may be accepted as things in themselves and therefore are free. Based on this picture, Ernst Cassirer comes to the following conclusion. By virtue of this doctrine, Kant can remain a strict empirical determinist and can nevertheless assert that precisely this empirical determination leaves the way open for another determination, different in principle, which he calls the determination through the moral law or the pure autonomy of the will. The two are not mutually exclusive in the Kantian system, but rather require and condition on each other. 9, page 202. The object investigated by natural science is thereby fundamentally altered, which Kant acknowledges in approaching this historical fact of natural science in terms of mathematics and experiment. They, all students of nature, learned that reason has insight only into that which it produces after a plan of its own. Reason, holding in one hand its principles, according to which alone concordant appearances can be admitted as equivalent to laws, and in the other hand the experiment, which it has devised in conformity with these principles, must approach nature in order to be taught by it. It must not, however, do so in the character of a pupil who listens to everything that the teacher chooses to say, but of an appointed judge who compels the witness to answer questions which he has himself formulated. The debate on determinism goes on, unfortunately, often below the level of Leibniz and Clarke or Bohr and Einstein. One major point is often neglected, although it had already been clarified by Kant's analysis. The observer and his perspective have to be taken into account. Cassirer expresses it by saying that after the decisive advance attained through Hume and Kant in the analysis of the causal problem, it is no longer possible to regard the causal relation as a simple connection between things, or to prove or disprove it in this sense. 5. Back to some roots of our problem. Motion in history. It does not seem to be mere chance that determinism is such a perennial. Indeed, the problem of describing motion can be traced back far as the beginning of ancient Greek philosophy. In this section, we will look at some of the oldest formulations of this problem, as well as two types of solution, Platonism and atomism, which are two of the main paradigms of subsequent Western natural philosophy and science. And looking back at the accounts given in the third and fourth sections of this epilogue, it will be noticed how each position achieves some balance between the two poles, represented by Parmenides and Heraclitus. Newton, for instance, utilizes atomism by letting his creator create indestructible, eternal corpuscles. See Newton Optics, Query 31, which, alongside the mathematical laws, explains the permanence of what lies behind the phenomenal world. At the same time, however, he is compelled to postulate the ceaseless intervention of God in the workings of the universe. The efforts of Leibniz and Einstein can be seen as extensive reformulations of Parmenides' unchanging one. Hume's work may be regarded as the attempt to balance the flux of sense impressions with the constancy of habit. Finally, in Kant's work, the role of the unchanging unity of the subject can be described as ensuring an identity-preserving fixed point in the face of the flux characteristic of all perceptual impressions. Similarly, consequent determinism in science represents manifest change in the context of immutable being. Although something is in motion, the motion itself is fixed according to deterministic laws. When viewed from a non-temporal perspective, such motion does not take place at all, and we end up with a Parmenidean denial of motion per se. Every mathematical description of motion attempts to reduce motion in this way. It is accepted as real on the one hand, but on the other hand it is represented in a medium, i.e. mathematics, that is itself considered incapable of motion. Let us return to our original question, the question of the relationship between mathematics and reality as it was described by Einstein. By giving the question a slightly different twist, our focus became less the precarious relationship itself than the historical dynamic underlying it. The bond linking mathematics and reality has repeatedly required reforging results, has in each case taken a different form from all previous linkages. It has become clear, at least in its rudiments, that with respect to this question, mathematics and metaphysics have developed a mutual dependence. But neither has dominated over the other. Both attempts ref to each other, and both will continue to rely on each other. It is thus not so much the relation of mathematics to reality that is ultimate of importance. What is astonishing and always worthy of discussion is that such a relation is attempted, and that it, in a sense that again and again needs to be redefined and justified, can be successful at all.